Have you ever heard of fault-tolerant measurement-based quantum computation? This is quite a long denomination to talk about a method for quantum computing that uses mostly local measurements. But most importantly, this method has a nice graphical translation that transforms complex quantum circuits into mere lines in a 3D setup. In this video, we present the basics of measurement-based quantum computation. And using this new graphical language, we develop new ideas to make it more expressive and performant. This project is a fruit of a non-local collaboration between Vancouver in Canada and Hanover in Germany. From the Canadian side, my name is Gabrielle and I'm a third-year PhD student at the University of British Columbia. I'm working in the Physics and Astronomy departments and at the Stewart Blossom Quantum Matter Institute.
Hello, I'm Marvin and I'm a second-year PhD student at the Leibniz University, Hanover.
Hello, I'm Robert Raussendorf. I'm Professor of Physics at Leibniz University Hannover in Germany.
Hello, I am Sven Bachmann and I'm a Professor of Mathematics at the University of British Columbia in Vancouver.
With this quite international team, we study a set of many entangled qubits on a 3D lattice, which we call the cluster state. Each qubit of the cluster will then be measured individually. Instead of just destroying the quantumness of the states, those measurements actually allow us to compute and process quantum information that is stored in a topological toric code living on the boundary of the 3D cluster states. This scheme is inherently fault-tolerant in the sense that due to the architecture of the state, the information is protected against noise, and most errors can be detected and corrected.
So here's a bit of background. Let's begin with something familiar: the surface code. The surface code is a stabilizer code. Some of its stabilizers live on sites of the underlying lattice, and other stabilizers live on plaquettes. When a stabilizer is not enforced, a hole is created. Specifically, not enforcing a site stabilizer creates a primal hole, and not enforcing a plaquette stabilizer creates a dual hole. For topological quantum gates, the holes are all that matters. First, in a pair of holes we can encode a qubit, but our setting is not just the plane, there is a third dimension. Our first question is, what does this third dimension represent? There are two viewpoints on this. First, with respect to the surface code, it is the time axis. The surface code is propagating in time. Or we may regard the whole block as a three-dimensional cluster state. In that case, the third dimension is simply one of the cluster axes. It is the second viewpoint that we take here in this video. The big picture is, a 3D cluster state is like a surface code propagating in time. Now let's put in some more details. We ask, what are these lines? What are the surfaces that stretch between those lines? And what's happening at the ends? Let's address these questions in turn. First, about the lines. They represent missing cluster. They are called defects, and they are made by local Z measurements on the 3D cluster state. Next questions. What are the surfaces for that stretch between the lines? In a nutshell, these surfaces represent quantum correlations. Specifically, the quantum correlations that survive the local measurements of MBQC. There's quite a bit to unpack here, actually. Let's take the microscopic view first. What we see here is the elementary cell of the cluster lattice. Qubits live on the edges and the faces of the elementary cell. Now to the quantum properties. The cluster state is a stabilizer state, and on the left you see one of its stabilizer operators. A Pauli spin flip X in the middle, tensored with 4 lateral phase flips Z. The resulting 5 local operator represents a quantum correlation of the cluster state. On the right, you find the very same correlation, but now endowed with a geometric interpretation. The central qubit lives on a face and the lateral qubits on the boundary of that face. In this way, cluster state stabilizers can be described by surfaces. Just to be clear, this geometric reasoning applies to all surfaces in the cluster. We have yet to clarify how the correlation surfaces become attached to the defect lines. We recall that on the surface itself, the correlation operator acts by spin flips x, and on the boundary, it acts through phase flips z. Of computational interest are the correlations that survive the MBQC measurements. In this regard, the spin flip x fits with the x measurements in the bulk, and the phase flips z fit with the z measurements in the defects. The upshot is, correlation surfaces of computational interest can end in the defects but not in the bulk. We are almost there, but there is one more thing to explain about the correlation surfaces. When we translate our lattice by half a lattice constant in either direction, then we map the cluster state to itself. However, the cell structure is not mapped to itself, as a corner becomes a center, an edge becomes a face, and so on and so forth. We find that there are two equivalent but distinct lattices that apply here, primal and dual. Remember this point. It will become important later on. As a consequence, correlation surfaces exist as primal and dual. Final question. What's happening at the ends? We observe that on the first and final slice of the 3D cluster, correlation surfaces end in the encoded Pauli operators of the surface code. And so, correlation surfaces transform incoming into outgoing encoded Pauli operators. Item number 5. We didn't initially have an item number 5 on our list, but we absolutely have to have it. Item number 5 is the examples. Our first example is really just a warm-up, the identity gate. The correlation surfaces that stretch along a pair of parallel defect lines convert a z into a z and an x into an x. That's the identity gate. And now the real example, the topological C0. This is what it looks like, a configuration of primal and dual defects intertwined. Let's look at the correlation surfaces that exist in this scenario. Here's the first. It transforms an incoming z on encoded qubit number 1 into a tensor product of two z's. We have 3 further correlation surfaces like this. The second surface maps z2 into itself. Surface number 3 takes x1 into itself, and finally, surface number 4 maps x2 into the product of x1 times x2. Together, we find these 4 propagation relations. The C0 affects them, and it is in fact the only gate that does.
Stabilizers, measurements, gates. This is the language of physics. But, as was already hinted at in the notations of the previous slides, all of this can be phrased in a pure mathematical language. Those who are mathematically minded may have already noted that the structure that arises in the microscopic discussion of measurement-based quantum computation in the 3D cluster state is that of cellular homology. Indeed, cellular homology is a way to describe bodies in any dimension by gluing together vertices into edges, edges into two-dimensional surfaces, surfaces into three-dimensional volumes, in such a way that the lower dimensional elements form boundaries of the higher dimensional ones. However, as is often the case, the physical realm is in fact richer than standard cellular homology. As pointed out, the cluster state represents in fact 2 homology theories that are dual to each other. We shall see shortly that this duality and its breaking plays a crucial role for us. However, a general mathematical understanding and a classification of such defects is currently not known. What is more, the macroscopic description of MBQC is in terms of a collection of knots, or more precisely tangles, and of the surfaces they support. It is a theorem of knot theory that any knot supports such a surface, a so-called Seifert surface. But in our setting, these abstract mathematical surfaces acquire physical reality, since they propagate quantum correlations and carry out the quantum operations. Here again, the presence of the dual surfaces creates in fact a richer structure that only awaits to be explored by mathematicians. It is also interesting to point out that the inner workings of the verifier, which will be discussed shortly, are exactly those that lead to proof of the existence of Seifert surfaces. All in all, from a pure mathematical point of view, topological MBQC is therefore a beautiful playground opening new avenues that only await to be explored.
Now we will see that we can play with the homology and break the lattice duality to enhance a computation. As a reminder, each plane in the cluster contains the toric codes. The planes that are alpha unit cell apart are dual to each other, meaning that their X Pauli operators and stabilizers are mapped to the Z operators and stabilizers in the other plane, and vice versa. The idea is to transform the lattice to its dual, but only locally. For that, we introduce a dislocation defect in the lattice. Let's first build a regular cluster state around a hole. The hole just corresponds to an internal boundary of our cluster, and the duality is still well defined. We can have a one cycle that makes a closed loop around the hole. But now we want to break this nice duality. And for that, we need to break the cluster. What we have done is torn the cluster apart, and we have put it together in such a way that the corner of a unit cell comes together with the center of another cell. It means now that for any physical qubits, whether this qubit is on a face or on an edge is a matter of perspective. The loop drawn earlier can no longer close following edges only. One end of the cycle is seen as dual by the other ends. Let's take the line on the top as a reference such that it stays on edges. The line at the bottom is then also on edges and it passes by the twist defect, and the qubits involved are now on faces. If this line is part of a pair encoding a logical primal qubit, then this qubit is mapped to a dual logical qubit. Now we can extend the defect to make a tube that's wrapped on itself to localize it. Only the lines and surfaces going through this area will be impacted by it. Two pairs of primal qubit lines are measured across a cluster. One goes inside the defect loop and is therefore transformed into a pair of dual lines that encode a dual qubit. Similarly, when the Z logical surface crosses the membrane supported by the defect, it is transformed into its dual counterpart, and thus encoding a logical X. A Hadamard gate has been performed on that qubit while nothing happened to the other encoded qubits. For convenience, we can transform back the new dual qubit to a primal one by untangling their measurement lines. Finally, there is a surface going from the logical Z on the left of the cluster to the logical X on the right side of the cluster, and vice versa. We can conclude that a Hadamard gate has been performed. Having now a useful set of fault-tolerant gates, we can think about implementing whole circuits on a larger number of logical qubits. Useful computation often use complex and long quantum circuits. Translating them to MBQC results in an intricate and huge measurement pattern. But those patterns are not unique and can certainly be simplified. And we have found some transformation rules to go from one pattern to an equivalent one. We applied them by hand to known and useful circuits, such as the one for magic state distillation. And for a few weeks, I put aside all physics and mathematics and just played with paper cubes and 3D drawing software to find an optimal structure and thus reducing the volume dramatically. I felt like being a designer. It was really fun and allowed us to really understand the transformation rules that could be applied. From that, we needed a way to verify that the new measurement patterns were correct.
While the correct application of equivalence transformations will always leave invariant the occurring logical operation, we would like to rule out the possibility of having made errors when transforming the circuit by hand. One method to do this is to simply consider the resulting circuit without its transformation history and check that the required correlation surfaces still exist. However, the resulting circuit will often be complicated, and so doing this retrospective check by hand isn't necessarily less error-prone than the original transformation. The solution for this is obviously to let the verification be performed by an algorithm. Given a circuit specified by a set of primal and dual defects, as well as a list of target vectors, the program should check automatically whether a surface supported by the respective target vector exists. How this verifier works under the hood is by observing that there exists a unique linear map, called the relative boundary operator, mapping an end chain to its boundary. Verifying whether a correlation surface exists for a given target vector then boils down to checking whether the linear system of equations has a solution. By the Rouge-Capelli theorem, this can be done by simply calculating and comparing the ranks of the coefficient matrix and the augmented matrix. This verifier allowed us to ensure that the complicated circuit constructed by us is indeed correct.
Thank you very much for your interest in our work. Here is a link to our paper where you can find more details about topological measurement-based quantum computation.